Hi everyone, you can hear me, right? Okay. I am Ananya. I am a final year PhD student at Notre Dame, working with Chris Hawk and Nicholas Lena. And today I want to start with just bringing your attention to this beautiful background image from JWST. And the reason is because if you look, okay, so probably you won't be able to see much, but I'll try my best. You can see many structures in this image, like these small clumps here, the clouds here, and more clouds here, structures here. So this stuff is in the disk of LMC. In the Milky Way disk, we have similar structures everywhere, but oftentimes it's really hard to observe them in the disk because of the high opacity. But in the disk halo interface, we can observe this structure much more easily. So the disk halo interface, we heard from Andy, from Jess, and from Theo. It's a region of extraplanar gas above and below the plane, roughly within 5 to 8 kiloparsecs, and it is supported by the matter and energy from stellar feedback through like galactic fountains, chimneys. So as this hot gas moves up from the plane, it will start becoming thermally unstable and break out into smaller structures like this, and those will cool to the final flow temperature. Between this hot and the cool phase, there is this intermediate phase. We call it transition temperature gas, but you can call it warm hot phase. The main point is this warm hot phase is very important because it provides most of the cooling for the hot gas, and it produces some of the important diagnostics like carbon-4, silicon-4, oxygen-6. And recently, McCord 2018, they found that these cooling structures must have some density-dependent size scales. And when these structures start to cool, any structure that is larger than these characteristic sizes will go through many fragmentation as shown in these middle two panels to reach this final size. So the main takeaway here is that the transition temperature gas at the disk halo interface density must have sizes of 10 to 100 parsecs in between that range. Now, how do we observe them? In the Milky Way, the only way we can observe the transition temperature gas is absorption spectroscopy. And here are some examples of different absorption spectra from the Milky Way ISM and the disk halo interface. And absorption spectroscopy gives us a lot of information about the line of sight structures. However, a single sight line cannot give us any information about the extension of these structures. To do that, we need multiple sight lines. And when we have multiple sight lines, we can get the absorption spectra, make pairwise comparison. For example, like when we have when we have two sight lines close to each other, they will prove same material, and we'll get the spectra, from the spectra we'll get the column density profiles, and the total column density for these two sight lines will see similar pattern. And for sight lines that are farther apart, they will trace different material, so we'll see different column density profiles and different integrated column density. So using this technique, we can get this angular scale over which column density from one sight line to the next will vary significantly, and that will help us to constrain the physical size scale of these structures. So this has been used by Hawk 2002 to see this variability, column density variability in the Milky Way disk halo interface gas toward LMC, and they're showing the column density variability as a function of angular separation between sight lines. And we see a lot of variability in different scales. The one limitation is that they didn't have enough measurements in this sub-degree scale, which is very important because later, Leonard and Hawk 2004, they found that toward globular cluster stars, which are separated by only 10 parsecs, they show no variability in the column density profile. So the O6 is not varying at all, or it's smooth at less than 10 parsec scale. So we need bigger sample at smaller or sub-degree scales, sub-degree separations. And that's where came the ULLYSES program, which is Hubble's Director's Discretionary Program. They have archived 400 UV spectra of OB stars in the Large and Small Magellanic Cloud. This is the Small Magellanic Cloud sample, and this is the Large Magellanic Cloud sample. And combining these two samples, we'll have 20,000 pairs probing the structures in the Milky Way disk halo interface gas foreground to the Magellanic Clouds on the size scale of 100th of a degree to 25 degrees. And the cherry on top is we have 3,000 pairs in the sub-degree scales, and that will give us physical size scale of 0.1 to like few tens of parsec size scales. So I have analyzed a high-resolution T spectra of the LMC sample, and here are some of my results. So here on the top panel, for each ion, I'm plotting the column density profiles with the median profile in orange for each ion, and then in the bottom panel, I have the median profile, 68% confidence interval and 95% confidence interval of these column density profiles for the cyclines that I have. And the first thing that we can see here is there is a lot of variability in this direction, in the direction toward LMC in this gas for each of the ions at every velocity, like at all velocity, there is a lot of variability present. And then we also see how the median profile is evolving with temperature. I'm sorry for calling O6 hot gas. It is not, but this is easier. And this is a qualitative look at the variability. And I have also measured the total Milky Way column density, which is the integrated column density between -50 to 80 kilometers per second. And for this Milky Way gas, here is this column density sky map. This is another qualitative look at the variability present in the data on the sky. So for each panel, I am plotting the coordinates of my cyclines, color-coded by the column densities that I have measured in these directions. And you can already see a lot of variability present in this small section of the sky. Especially for this 2 degree patch, for each of the ion, you can see in some cases there are the highest column density present and also some of the lowest column density present, which is giving you an idea of how much variability is there. So let's quantify this. So here in each panel on the y-axis, I have the log column density difference plotted against the angular separation of these cyclines. I'm not going to talk much about aluminum-3 because not much data, but for silicon-4, carbon-4, O6, we see some trends here. In the inset, I'm showing the sub-degree scale variability or sub-degree scale data. At sub-degree scale for carbon-4 and silicon-4, we see that the range of variability is smaller compared to the rest of the separations. So as the separation increases, variability starts to increase, the range in variability starts to increase. For O6 though, variability is same at all separations. So that's interesting. And I have also measured the autocorrelation function, which is statistically telling me the amount of correlation there between one measurement here and one measurement there. And what I'm seeing here is that at sub-degree scale for carbon-4 and silicon-4, there is a little bit of signal telling me that there are structures at sub-degree scales in this direction in the carbon-4 and silicon-4 gas. Whereas for oxygen-6 at sub-degree scale, there is no autocorrelation present. So this might mean that oxygen-6 probably the autocorrelation is on a larger scale or whatever. I don't know yet because I haven't explored the whole data set yet. So that's for next. So I'll just leave my conclusion slide here and take any question.
Thank you. questions for Ananya?
I was wondering, unless I've misunderstood one bit, because I think Jess earlier was talking about carbon 4 being coherent on kind of considerably larger scales, and I'm wondering how that checks with what you've just spoken about here.
So, okay, oh, carbon 4 is here. So these are on a, like I'm probing very tiny scales. So there is, even though carbon 4 is coherent in 2-degree scales, like there is still variability. In that patch, there can be variability. So this, not necessarily the, it can be in the same structure. One patch is a tiny bit denser than the other part. So because these are really small scales, yeah.
And just to follow up on that too, because that is like something we address in the paper, and we do find there is some variability on sub 2-degree scales in Hannah's paper, in the Quastar paper, right? So it's not as simple as, it's always coherent on 2-degree scales, right? So it is more complex than that for sure, and I love,
It's the difference between like a cloud, one cloud here, one cloud there, versus like in the cloud there is clumpiness. So, yeah.
Andy?
I may have missed this, but are you talking about low velocity gas when you're looking at these differences between silicon 4 and carbon 4? Is this all not high velocity clouds, but low velocity ISM
Just the
gas?
Milky Way low and intermediate velocity.
Low and intermediate.
Yeah.
Okay.
Haven't looked at the high velocity gas
Okay.
yet.
Yeah, because I wondered if any of this depends on the velocity. Like, does the amount of variation change as you go up to higher velocity?
Yeah, so here I'm just showing the average over the Milky Way, but I have those results too. Not here, but yeah, I'll have those too. There is variability though, even on those on those separate components at the same scale.
Yeah. Any other questions? The last one?
Yeah, for these sidelines, do you see variability in H1? If you have few
I
spectrum, you'll be able
haven't
to
measured H1. That would be interesting. You mean H121 anyway?
No, you can use few spectrum. If you have O6, you'll have.
Oh, I haven't measured H1.
It's harder. It's very hard.
All right, let's carry the conversation to coffee and breakfast behind. Thank you.